we have two issues. One is the very constraints which are maybe insufficient constraints. We may give insufficient constraints or over constraint models. Okay, so insufficient constraints the program won't solve. So there is no issue in it. Definitely, user has to work on resolving that issue. But the over constraint models, we need to see how to remove that over constraint models. Okay, because the reason is the over constraint model always tend to give maximum means inaccurate results. Okay, so the inaccuracy we need to remove by making it to minimum constraints required for any given problem. So in minimum constraints required, generally we need to see how can we give the minimum constraints to avoid rigid body motions in 6 directions. So for any component, okay, in general, any component can have 6 degrees of freedom, 3 translations and 3 rotations. I'm not talking about element, I'm talking about general component. So the constraints which we give should restrain this rigid body motion. Okay, and also these constraints should represent actual physics of the problems. If both the things are solved, means then these minimum constraints are can be used for the simulating the problem. So one of the common check we generally use whether the model is properly constrained or not is we use elevated temperature. We'll apply elevated temperature to the model and check whether results any stresses are generated. If any stresses are generated, then model is over constrained or not properly constrained. If there are no stresses generated, then model is properly constrained. So we studied in our earlier college or like BTech first year or second year. So free thermal expansion will never result any stresses. So in general, any model in the universe should have free thermal expansion. Nodal coordinate system. This again I'll discuss when we look into the applying loads. So constraints are also used to simulate a symmetric basis. We understood what exactly symmetric bases are. So symmetric we can use for symmetric as well as anti-symmetric basis. So if you see this typical example plate with a hole, so we can simulate instead of complete geometry, we can simulate only 1/4 of the geometry and the cut faces. Okay, these are the symmetric faces. These faces we can constrain. This face, suppose this is x direction and this is y direction. This face is constrained in x direction and this face is constrained in y direction. So this the direction normal to this face need to be arrested here. That direction normal to this face need to be arrested here. So this is how like boundary conditions are used to simulate symmetric basis as well. So this is one example. Again, we'll discuss in our loads and bases. Here I would like to discuss. So here the constraint nodes at 4 locations separated 90 degrees apart, and hoop as well as circumferential direction. So we should allow free radial growth. So we should not arrest any radial constraints for this type of problem. This is cylinder. This is a rotor with subjected to the angular velocity. So if you see here, it is this is a radial deflection plot. RCS one is a cylindrical coordinate system, and the EX is radial deflection. So here, if you see, it is free. Rotor is freely expanding as it moves from inner to outer dia. Okay, so inner dia is having maximum expansion, and that outer dia is less expansion. The reason is because of centrifugal force. The stresses will be mainly generated because of centrifugal force. So, so basically, we'll be having hoop and hoop stress. For this type of loading, generally it is subjected to hoop stress, and inner dia is subjected to high stress here. So I think there is issue with the screen sharing. Yeah, just I will quickly glance through again. So, so in general, we should avoid rigid body motions in our stress analysis problem. Otherwise, it may cause errors. Means it won't solve, the model cannot be solved. So typically, the rigid body motion is purely because the stiffness matrix still a singular matrix. So singular matrix, if your stiffness matrix is singular, and that won't give any results. So we should have a constraints in the geometry to remove the singularity in the stiffness matrix. Okay. So when you try to solve a model which is having a rigid body motion, generally we'll get a errors. The errors are listed here. So different programs will give different types of error, and the run will be terminated. So we cannot get any results. So in few softwares, results are displayed, but and displacements are very large. Okay, so generally rigid body motion things will get a error. Most of the programs will get error. So to avoid that, we should give constraints of constraints in the model, and those constraints should be minimum constraints. That means we should not give over constraint to the model. There should not be any over constraints in the model. The over constraints will result into inaccurate stress. So a model should be properly constrained. Okay, means it should have very minimal constraints, and if you have improper constraints, either minimum less than the minimum required, or it is war constraint, the the results generated due to war constraint model are purely inaccurate, and there won't be any results generated if it is improperly constrained. Means, uh, constraints are less than the minimum constraints. So, so minimum constraints are we should be able to give minimum constraints to the model. So some of the examples on 2D aspects are listed here. You can review it. I'll provide this document. So generally, what exactly minimum constraints? What minimum constraints should do? A minimum constraint in the model should ensure that it will restrain the rigid body motion of a particular component. I'm not telling about elements. I'm particular component. It's in three directions in rotation. That means it should restrain the rigid body motion in 6 degrees of freedom. So this is about nodal coordinate system. Nodal coordinate system I'll be talking again when loads and when I will be discussing on loads. So on symmetric basis, uh, constraints are used to simulate this symmetric basis. So we have two options, two things. One is on symmetric and another is on anti-symmetric. So for both the things, we can use bound displacement constraints to enforce symmetry or anti-symmetry. So coming to um, So coming to typical plate with a hole, this is standard problem which we use in stress analysis. This plate with a hole, we can model complete geometry, or we can model only 1/4. Okay. So while taking 1/4 model, so here there are two cut faces here. So one cut face we can arrest direction normal to the face. So the direction normal to this face is x direction. Okay, so this face need to be arrested here. Similarly, direction normal to this face also need to be arrested. That is, for this face, y is the normal direction that needs to be arrested here. Maybe tomorrow I'll show this example, how close, how accurate while simulating with the 360 degrees model, complete model versus 1/4 model. So this is one more example. This is a hollow disk subjected to angular velocity. So these are the geometry details. Material properties are given here. So here we have used very minimum constraints. So minimum required constraints we have given. So we arrested 4 nodes separated 90 degrees apart, rotated in 90 degrees. Okay. And these nodes are constrained in axial as well as circumferential direction. And we should not arrest in radial direction, because radial direction to grow radially free. We should allow this to grow radially free. So if you, after analyzing, if you see here, this is the plot with the deformed and undeformed shape. There is a radial growth in the component, free radial growth, and we see there is a radial displacement which is uniform throughout 360 degrees. So these constraints are not causing any unnecessary stresses. Okay. So even if you see the stress plot, these stresses like S1 as well as hoop stress. Hoop stress is stresses in circumferential direction, are caused mainly due to centrifugal force, and we are not seeing any inaccuracies here. The stresses are accurate and they are very uniform throughout 360 degrees. And both, if you see, the both stresses are same. That means the maximum stresses, maximum tensile stress, S1 is represented as a principal stress, principal tensile, and they represent as a maximum principal stress. That means all stresses are tensile. So it is 171 KSA. If you see here, here also 171 KSA. The maximum, the tensile stress is caused mainly due to hoop stress, and this hoop stress is because of centrifugal loading. So any questions here? Any questions? Generally, we have various types of loads, which includes point loads, surface traction, that is also known as pressure, body force. These are the main loads. So body forces and surfaces, generally like body forces and surfaces will be converted into nodal forces. Let us understand what exactly those things. Okay. So if you see a final assembly of a force matrix, that consists of 3 points. Okay. So first point is this one is body loads, this one is point load, and this one is uh, pressure load. Okay. So these three comprise of uh, global nodal forces vector. Okay. So coming to surface forces consist of this equation. So where Ts is the surface traction and Ns will be the shape functions for the evaluated along the surface. Okay. Similarly, like body forces maybe arise due to body weight or angular velocity. Typically, these things are called as body forces, and they are evaluated as using this equation, where n is a function of x and xyz locations of the uh, each uh, each point. So let us understand what exactly is the body force. Suppose I have a cylinder subjected to rotation. Okay. So I have a cylinder subjected to rotation. So so each node, okay, in this component, every node will be subjected to omega. That means there will be force coming from rotation. Okay. Typically, it is called mr omega square. Okay. So where m is the mass. So each node there will be force acting resulting from the rotation. That is called centrifugal force. So similarly, suppose if a bar subjected to gravity load. So each node in the bar will be subjected to gravity load. That is m into v, where m is the mass of each node. Okay. So typically body forces consists of centrifugal, for angular velocity, and gravitational forces. And since it is a point rate, it's on one node rate. So basically depends upon x, y, z locations of the. So one typical example, rotating flywheel subjected to an angular velocity. The body forces uh, will be rho r omega square. Okay. Similarly, gravitational force, okay, minus uh, rho g. Okay. So this rotating flywheel is subjected to angular velocity as well as gravitational load. So those nodes are subjected to two types of loading. One is radial direction, another in axial direction. So radial direction is the resultant of velocity, and axial direction is the resultant of gravitational force. A cylinder is subjected to internal pressure. Okay. So here the pressure, internal pressure, we need to apply pressure inside. Okay. So this is for 3D model. If you would like to consider only 2D model, So we can take this section. So we can solve 3D problem or as well as 2D problem. Okay. This we have discussed. This is types of body forces, and so a force is a so force we can apply multiple ways. A force is a concentrated load that you can apply at a node. Point loads such as forces are appropriate for line elements such as beams, bars, and springs. Okay. In solid shell models, point loads usually cause clarity, but are acceptable if you ignore stresses infinity. So, typically, if you want to apply load on one node, we should apply only on this 1D elements like beams, springs, and spars. If you try to apply 3D model, we may get similar stresses. Let us look into it. Suppose I solved a model by applying force of 100 newton on one node. So if you see here, so typically we can using hand calculations here. So from here, if you calculate stress, it is nothing but it will be 10 MPa. So when you see here, the highest stress is very high, close to 3000 MPa. So if I unselected some locations here, then we got very hand calculated value of 10. So in the area of vicinity where load is applied, we will get singularity, but away from that we may get accurate stresses. But in general, we should avoid this type of loading. So how to then the important then what is the important understanding here? We should avoid applying load on node. Then how to apply load on node? Load on that area. So one way you can do it is apply distributed point load. So what you can do is instead of applying on a node, so you count number of nodes on this cross section and load by number of nodes. Apply that value on these nodes. Okay, so that is one way. Then second best method out of which is pressure mapping. So what you can do is you can calculate the area, load by area, you can directly apply the pressure. Okay, so this will result perfect. That only why it is not perfect is so there is some theory behind it. Why load number of so suppose I have a 3x3. So this is our let us take small example. 3x3. Okay. So if you see here, generally when there is a load we need to apply on this say load on node. Suppose I need to apply P on this. So load should be P. Then generally like one method is number of nodes. You need to count 1, 2, 3, 1, 2, 3, 4. So total 16. So load on each node will be P by 16. So we need to apply P by 16 on each node. But in general, this node is shared by only one element. This node is shared by two elements. So which is not correct. So what we need to do is we need to divide instead of load on node, we should divide load by number of elements. So we have only 9 elements. Then total load on each element is load by 9, P by 9. So yes, we need to apply P by 9, here P by 9, here P by 9, here P by 9. So again this P by 9 will be divided into 4. Okay. So P by 30, P by 36, P by 36, P by 36. So there will be P by 36 for this node. For example, P by 36 is coming from, so here P by 36. So this node is shared by two elements, this element and this element. So it will be having 2 P by 36. Similarly, this node is shared by 4. Then P by 36 into 4. So here it is shared by 2. 2 into P by 36. So this is how we need to distribute. So it requires lot of hand calculations. So, there is one, this distribution requires a lot of hand calculation, and it is a time consuming. Whereas simply calculate area, okay, then apply P by A, load by cross section area, apply it as a pressure. So this is having more simplistic and best of smart technique. So we should avoid most of the time applying distributed load. Okay, so that will reduce lot of hand calculation. So this is calculating load by number of nodes is an approximation. It's not perfect, but this is load by area is perfect. Okay, and smart technique, quick and fast. So coming to pressure mapping, once you map the pressure, always we need to check whether you are applying positive pressure or negative pressure. Okay. So the positive pressure will always, pressure is like pressure on a component is pressure, acting on the component, that is a positive, and when you want to apply pressure away from the component, then you have to apply negative pressure. Okay. So this is the example we discussed earlier. I'll skip this. And coming to second example, so to analyze the overhang bar with self weight. So this is to understand what exactly is the body loads. So here this overhang bar is subjected to gravitational load or self weight. So these are the dimensions. This is the material properties. So here this face is constrained, and we applied a gravitational gravity of 9.810 mm per second square. So when you try to solve, we got a axial deflection, means deflection along this length, that is this value. So let us understand what is the total weight acting on it. Okay, so total mass is given by this one, 7.9 U. So same density we have calculated, we got this value, total mass. From density we got total mass, and then self calculated mass into gravitational, we got this one. So this is the load acting on the component. Okay, so we can check the reactions when I try to check the reactions at the constraint locations. Okay, so equal and opposite reactions, right? For Newton's law. So when we try to check the reactions, we got this reaction. So it is matching with the total self weight. This is one example. Okay. So now coming to third topic of our fifth chapter, couplings and constraint equation. So actually most of the things will go hand in hand here. So first I would like to discuss more on this coupling and constraint. So in the meantime we can see couple of case studies. So in last session we saw like how contacts are used to simulate interface components. So and apart from contacts, we also have some options. So contacts will bring a lot of complexity to the model. So in some of the sometimes it may not be required to simulate contacts between the interface components. So to reduce the runtime, we have other techniques to connect the interfacing components. Those techniques are we can use either couplings or constraint equation. So generally contacts are more accurate. Couplings are generally used for coincident nodes, means the node should be coincident, and constraint equations we can use for dissimilar machines. So basically couplings or constraints are very like user friendly generally, and basically what we need to do is we need to establish relation between two components. Okay, so in terms of displacements. So what we need to tell is, like if you see here, there are two components here. There are two tubes. We take this cross section. So there is a overlap between the two tubes. So here, in actual physics, they are together. But how to simulate this one? One option is you can put contacts or you can use couplings or constraint equation. So here what we need to do is we need to, if you want to use couplings or constraint equation, that means you need to establish a relation between these two components. The degrees of freedom you need to establish. Okay. So, what you need to tell is like the interface of these two components should behave similarly because they are tied together. Okay. So when you try to um, solve a physical cantilever problem, so this is one cantilever and it is subjected to point load. So this should be deformed in this way. So at this interface, it should be if they are together, they should be deformed together. The deformation between this component and this component should be same at the interface. So that relation we need to establish using couplings and constraint equation. So when you try to solve this problem without any connections between these two things, so you applied load, you applied constraints, and when you try to solve, you will get rigid body motion. Okay. The main reason is there are no constraints acting on it because this component and this component are not tied together between these two components. Okay, then it will cause rigid body motion. So the stiffness matrix associated with this will be singular and we will get a rigid body motion. So to establish relation between these two components in degrees of freedom, we can impose coupling equation. Then if you try to solve, it will converge. So if you see here, one of the important thing when you try to put couplings, the mesh pattern should be same on at the interface location. So the geometries are same; they are not connected. Okay, there are two independent components, but we need to enforce the coupling. So what we can do is like we need to enforce. We should have a proper mesh pattern and at the interface areas, and we can put a couplings. So we have put a couplings here. If you see here all the green locations, all the green points are couplings. So we put couplings here with proper mesh pattern. This is also another view. So this is the axial view, and radial view also. We have all the nodes are tied using coupling. So when you try to solve the model, so a deformation plot here, and if you see here, there is no discontinuity. The deformation is full of continuity here. There is no discontinuity. That is because of couplings. So let us look into the deflection plot, deflection results at the one of the location. So this node, and if you see the arrows, this arrow and this arrow, both are same. The nodes at same location, but on different components. If you see the displacement values along y direction, both are same. What does it mean? So it says that the deflection of one particular node should be same as deflection of other node. So I have two nodes here. Let's take here. I have two nodes here. Node 1 on this component and node 2 on this component. So we put a coupling here. That means the deflection of this node should be same as deflection of this node. So that is the relation we are imposing by putting a couplings. So we need to put couplings. Suppose this component, this element, if it is solid element, solid 8-noded brick, 8-node solid, we need to establish relation in 3 directions. Each direction, one coupling. So 3, if you want to establish, then we need to use 3 couplings in 3 directions. So one coupling can be given only in one direction. Suppose you want to establish relation in 3 directions, US, UY, and UZ, then you need to give 3 couplings. 3 couplings you need to give between node 1 and node 2. So coming to some of the important things on couplings or constraint equations, the constraints should be only given applied to master node. So in general, like when you try to use constraint equations or couplings, so program either program will choose or the user can choose which one can be the master. Okay, so master, we can give constraints only to the master node. So constraints means suppose if you take one particular component, or we can see one example. Yeah. So let us take this example. This is called a spin joint. So here we need to give a coupling here between these two things. And once you give this coupling, you need to constrain this node. You have to constrain this node. So in this condition, definitely we cannot give any. We need to ensure that this node should be master node. So if this node is a master node and you are trying to constrain here, then it won't solve. The program won't solve, saying that it's an issue with the master and slave nodes. master node should always be driving the slave nodes. So constraints should always be applied to the master node. Constraint equations are more general in that user can write equations uh, that express an arbitrary relation between among the nodal unknowns. Uh, so user can write his own equations to establish a relation between two nodes. Suppose if I want to establish node 1 and node 2, you can view the relation between these two things with the user defined unknowns, which we can discuss later. Okay. Constraint equations are used for a variety of applications. We can use for connecting dissimilar meshes. We can model interference feeds. Connecting meshes have different degrees of freedom. So we can, as you know, like a solid is having 3 degrees of freedom. Solid element shell is having 6 degrees of freedom. So we can use constraint equation to connect these type of different element types, and we can use modeling of rigid regions. So we can use in this problem, this is a brick mesh and this is a tech mesh. So definitely we cannot get the same mesh at the interface. So here for this type of problem, we can go for constraint equations. So if you see the difference between couplings and constraint equations, we are not seeing much difference between both the things. So here we have uniform mesh pattern. Here we have different meshes here. So that's the reason we have used constraint equation. The deflections more or less same. So more understanding on coupling and constraint equations. Coupling and constraint equation generally acts like a elements and they increase the overall finite element problem. So that means it increases bandwidth and wavefront of system of equations. It will generate additional equations to solve the finite element problem. And it will increase the overall, it will increase computational effort. Constraint equations fed to the solver that describe relations between degrees of freedom. Basically, it will have a relations. So in constraint equations, we can establish a relation. Suppose in node 1, node 2, we can establish a relation. That we'll discuss in upcoming slides. So how we can define the relations we can discuss. So in couplings, generally the degrees of freedoms are equal. The deflection of node 1 should be equal to deflection of node 2. That is defined in couplings. So multi-point constraints, no equations written by users. So when you use the multi-point constraints, it's like creating a additional thing. So no need to write any equations. So program will automatically create a multi-point constraint. So when it is solving, it will write all the necessary equations. So, so this we have discussed on degrees of freedom. So degrees of freedom affect on nodal coordinate system. So basically, for any node, especially in ANSYS, typically all nodes are having nodal coordinate system aligned to the global Cartesian. Okay. So in ANSYS, default coordinate system is Cartesian coordinate system, global Cartesian coordinate systems. So all nodes will be having Cartesian nodal coordinate system. So if you see here this picture, so all these nodes are aligned to the Cartesian global Cartesian coordinate system. Suppose we need to establish a coordinate system such a way that all nodes. This is a circular cross section. That is assume. So all nodes should be aligned in global cylindrical coordinate system. Then what we need to do is we need to rotate these nodes along the global cylindrical coordinate system. So if you see here, x is a radial, y is a tangential, and z is a axial. So if you see after rotation, all nodes are aligned along the global Cartesian. And this nodal rotation or nodal coordinate system is very, very critical for some of the stress analysis, especially when you are doing some cyclic symmetric type of analysis. So not only global cylindrical or global Cartesian, you can create your own coordinate system, and you can align the nodes as per the problem or work requirement. So coupling is a way to force a set of nodes to have same degrees of freedom. That's what we discussed. Similar to a constraint, except that degrees of freedom value is calculated by solver rather than user specified. So here, coming to the same coupling. So we are constraining here, and we are applying load, and we are using constraints. Give me 1 minute. By solver rather than the user specified. Another 5 or 10 minutes. So generally, like if you take a typical cantilever tree and if you try to solve it, so K matrix will be singularity will be removed because we are putting constraints here. So here we are putting a couplings here. Okay. So here we put constraints. So this K matrix is singularity is removed because of this constraint. This K matrix, the singularity is removed because of this coupling. Because of this singularity matrix, the deflections are calculated at this location, and these deflections will be informed this location. So at the end, this stiffness matrix will be non-singular, and overall model will be avoiding that rigid body motion. So this is what it is explaining here. Similar to constant, except that degrees of value usually calculated by solver rather than user specified. So here, degrees of freedom will be calculated by the solver at this location because of coupling. A coupled set is group of nodes coupled in one direction. So common application, enforcing symmetry. We can use enforcing symmetry, frictionless interfaces, pin joints to model sliding at the blade and disc interface. We can use. So coming to enforcing symmetry, this is a disc or rotor, we can call it as. So we can take one sector instead of doing 360 degrees model. We can take one sector and do the analysis. So here, we can put the nodal base on the two symmetry of the edges in all degrees of freedom. So here, what we'll do is generally, like we'll take the cut faces, we'll match the mesh pattern at the cut faces, and we'll couple these cut faces nodes. So that will enforce the symmetry. Let us understand some simple problem on this enforcing cyclic symmetry. So this is the geometry details. So inner dia, outer dia, and there are number of holes here. So number of holes is 30. So this is 360 degrees model. So we can take it as a one sector here, equivalent sector. So in 360 degrees model, as we discussed earlier, we can constrain 4 nodes in axial and circumferential directions. In cyclic symmetry, couplings, we enforce couplings here. So So here we need to select the node, mesh pattern need to be matched. So what we need to do is we need to select the node on this subsector. So cylindrical we need to rotate this node in cylindrical coordinates. That means each node should be in the radial direction. These nodes as well we need to rotate in cylindrical coordinates. So once you rotate the node, you need to couple these two nodes in 3 degrees of freedom. This node and this node you need to couple 3 degrees of freedom. That is three couplings: ux, uy, uz. Like that, you need to couple individually. Okay. This is how we can enforce cyclic symmetry. What it says is the deflection and the deformation at this node in 3 directions should be same as here. That will enforce the cyclic symmetry. And apart from that, we need to arrest one node at the center in axial and avoid any split motion. So when you try to solve this model both 360 degrees as well as the cyclic symmetry, if you see here, the results will be more or less similar. There is no deviation at all. Okay. So we are not observing any changes. Have a close look here. Stresses we are observing same stress 185 kSA here also 185 kSA. So we are getting a max stress at the hole at this location, and if you see here we are getting max stress at this location, and there is no deviation in the overall stress pattern as well as max stress value. So I would like to stop this session at this point. Tomorrow we'll continue again. So if you have any questions, please raise.